So let's start from the point where we have stopped yesterday. We have discussed what do we mean by signals, right? So who can say? Signal, it is a function of one or more number of variables that contain information. Right? So we have defined it as it is a function of one or more variables which contains some information. So I told you that information is nothing but the amount of uncertainty associated with an event. And we have taken few statements which happen to be some mathematical statements, some universal truth, and some incidents out of which we predicted what is the amount of information that it has. Right. So such type of information are gathered with respect to time or with respect to some other variable, and the signal is framed. And such type of signals are passed through some communication channel or medium to the receiver to convey the information. Right. In communication system, I told you an example of a system, right? So I take a communication system, so which is having basically three parts. One is called as transmitter, and another we call it as channel, and the other part is the receiver part. These three are the mandatory three things that we should have in a communication system. So in this system, the transmitter will be transmitting some signal, right? So it will be transmitting some signal, maybe x of t, and this signal is passed through this channel and reaches the receiver end. And at the receiver end, we mathematically write it as y of t, which happen to be the received signal, which should be similar to x of t, but practically it is not x of t. Right? So this is a system like say this part, this yellow part. So it takes a signal as input, that is, it takes x of t as a signal as input and produces y of t. So the system takes some signal as input and do some sort of operation on it, and we produce another signal at the other end. So this example I had given last time. So today we will see, I mean, signals, how they are classified into and what various categories of classifications exist, but we will discuss. Right. So up to this point we have discussed in the last class, and let's say I will write signals. I have, let's say, one-dimensional signal. Okay. Example, one-dimensional signal means, yesterday I gave an example, temperature versus time, or let's say today I'm giving an example, amplitude versus. Let's say I'm speaking and my voice is being captured using a device called as microphone, which converts my speech signal into some form of electrical signal, and that signal is communicated to you. Okay. So let's say one-dimensional signal, example, right? So right, voice signal is an example of one-dimensional speech signal, voice or speech. Voltage signal, current signal, electromagnetic waves. These are examples. Okay. So let's plot it how it looks like. I have randomly plotted it. For each value of time, you can see for each value of time, there is some y-axis value associated with it. Right? For each value of time, we see some y-axis value present. And it is not the case always. We have types of signal for which for every x-axis value, the y-axis value is not present. We call such type of signal as discrete signal. And if the x-axis happen to be time, we call it as discrete time signal. So this is an example of one-dimensional signal. Right? So in one dimension, uh, we only represent the amplitude, the temperature, or the voltage, or the current. So let's check for two-dimensional signal. Example, we will see two-dimensional signal. In two-dimensional signal, example I'm giving, you have, let's say, video signal. In 1D, one-dimensional, you can have noise, speed, movement, voltage, current, electromagnetic wave. So two-dimensional signal, you can have video signal which consists of multiple images, right? Images can be considered as two-dimensional signal, right? So video signal you can take as a special form where one more dimension is added, right? So you can call it as three-dimensional signal. So in two-dimensional signal, you have like an image, and you have x-axis, y-axis which contain either the red, green, blue RGB values or the grayscale values at different pixel positions, and several such images taken at different rate. Like video signal is what continuous images if you have, and if you play them at a given rate, you feel that it is a video signal. Right? So video signal is many images, they are played at different rate with respect to time. So here we can call it the video signal as a 3D, three-dimensional signal, and the two-dimensional signal will take consider it as a image. Okay, so one-dimensional signal here various examples. Okay. So this is one sort of classification. Two-dimensional signal means we can say when a function depends on two independent variables to represent a signal. The two independent variables, so the black and white image you can see with respect to two independent variables which we represent it, we call it as a two-dimensional signal. If you have more than one number of dimensions or more than two number of dimensions, we call it as multi-dimensional signal. Next type of classification is signals can also be classified into two types. Let me write continuous time signal. The other one is discrete time signal. So when I say continuous time signal or discrete time signal, it indicates that x-axis is time. Okay. So the independent variable is time. Independent variable is time. Okay. So when the independent variable is time, so whatever we represent with respect to time, call it as continuous time signal or discrete time signal based on some property. So what are those properties? Let's discuss. Continuous time signal. It is usually represented. Signal is function of the independent variable, right? So let's say we write it the variable or the function name is x. Okay, I have taken small x here, and in bracket I write small t. It represents what? This is the function. X is the function, and this happened to be the independent variable. Right? This x is the function name. This is the function name, and this is the independent variable name. Independent variable name. Okay. So we can write x of t, or you can write s of t, whatever, like y of t, r of t, anything, anything of t. It represents what? This is x-axis is time. Okay. So let me draw here one signal. This is y-axis. I take x-axis to be time, then let me take y-axis to be some amplitude. It may be voltage or current or anything, and I will draw it like this. It looks like a sinusoidal signal. Right? It looks like a sinusoidal signal. Just I have taken one random example. So here what happens, you see, for every value of time, you can see for every value of time within a given range. So t, let's say, is 0, and I write it as 1, write it as 2, 3, 4, 5 seconds. Okay. So within 0 second to 5 second, how many values are there? Let's say in between 0 second to 5 second, how many values uh, are permitted? You can take how many values in between this range, 0 to 5 seconds. How many possible values are there? 25. Answer. Yeah, am I audible? Someone speak. Roll number 25.
Yes, sir, it's
23.
audible.
It's audible, right? No. 33. Srivastav.
Yes, sir.
Answer. 0 second. In between 0 to 5, how many values are there?
Sir, 4.
4. Like 1, 2, 3, 4, you are saying, right?
Yes, sir.
Not in this figure. In general, in between, let's say I write some time bound, let's say T1 from T1 to T2. Let's say I write this as T1, write this as T2. In between T1 to T2, how many values can exist? Not in figure, in general.
Infinite.
Infinite values exist, right?
Yes. Yes.
So there are infinite points over here. Okay, there are infinite points over here, and for each point, we can see a y-axis value present. Take any point here. Take any point here, you can see a y-axis value present, isn't it? We have some amplitude value associated with each x-axis value. Such type of signal, we call it as a continuous signal. Okay, whereas the x-axis happen to be time, and if a signal satisfy this property, we call it as a continuous time signal. So you can make a note that for each x-axis value, y-axis value is present. Then we call it this type of signal as continuous signal. I guess it's clear to all of you. For each x-axis value within a given bound, right? Within a given bound, it's if someone asks you in this figure, what is the value of the signal at t is equal to 6 seconds? You cannot say, right? It's not defined. At t is equal to, the things are defined up to t is equal to 5 seconds only, right? Up to this point only it is defined. Beyond this, we don't know. So if I write this signal mathematically, x of t, let's suppose, so I can write x of t is a sinusoidal signal, and let me write this this peak of the signal as a. Let me write it as a sin equal to t is the mathematical expression of this, and from t lies between what value 0 to 5 seconds. We write mathematically this figure in this way. So what is this? This is the function name or the signal name x of t. Mathematically, how it is expressed? It's a sinusoidal signal. A happen to be the amplitude. A sine 2 pi f t. This is sine theta, right? So this theta, I have written it in terms of the angle, right? 2 pi f into t, and the t lies between 0 to 5. And for each value in between 0 to 5, when t lies between 0 to 5, for any value within 0 to 5, there exists some y-axis value, right? There exists some y-axis value. So whatever t you put, t if you put here 0.5 also, you will get the answer. T if you put here 4.9 also, you will get the answer. For any value of t, if you substitute, you will get the answer. So what is this f frequency of the sinusoidal signal? Frequency is nothing but inverse of the time period, right? This is 1 upon capital T, and capital T happen to be one complete cycle. How much time it takes? This is capital T second. Later we will see this. So this T is nothing but equal to 1 upon F. So this F is nothing but 1 upon E. So it's a constant value for a given. So mathematically, we have expressed a signal here. The signal what I have plotted, mathematically it can be expressed in terms of x of t is equal to a sine 2 pi f t, where t lies between 0 to 5. What this will be. So this is an example of continuous time signal, or continuous signal in the sense, continuous means within a given range, infinite possible values can be assumed. So you should remember this with this continuous means within a given range, infinite values can be assumed. It may be in the x-axis, it may be in the y-axis. So current example is the signal is continuous along x-axis, or the signal is continuous along time axis. That's why we call it as a continuous time signal. The signal is continuous along time axis or x-axis. That's why we call it as continuous signal. So continuous means what?
Given range has infinite values.
Infinite possible values within the range. Within the range. In given range. So it can be in any direction, x-axis, y-axis, z-axis, or any axis. Right? If in that axis, within a given bound, infinite possible values it can assume, then the signal is said to be continuous along that direction. We have learned now a signal that is continuous along x direction or x-axis, or a signal that is continuous along the time axis. That's why we call this signal as continuous time signal. It means what? For each value of time within 0 second to 5 second in this figure, we have some y-axis value present. So whatever may be the value, we have some y-axis value present for every value of x-axis in the given bound. It is called as continuous time signal. Look at the remember this. Next, we will see discrete time signal. So in the similar way, we can express discrete time signal. Can anyone answer? Discrete time signal. It means what? Discrete means
Yes, sir. For some values of x-axis, there
yes.
might not be y value.
Discrete means within a given or within
Not
a,
continuous, sir. One
within a given range, few permitted values will be there. Not infinite. Okay. A few permitted values are there. Right. So let's say I'm taking one x-axis here. This is time axis only, and this is amplitude axis. I'm specifying here few values of time. So let's say t is equal to 0 second. So 0. I know the value at t is equal to 0.5 second. I know the value at t is equal to 1 second. I know the value at t is equal to 1.5 second. I know the value at t is equal to 2 second. I know the value at 2.5 second, 3 second, 3.5, 4 second, 4.5, and 5 second. So at these instances, I know the value. So let me plot it in this way. We have some value. Don't compare it with the last figure. I'm just giving some random values to it. Like this. So what is visible from this figure? X-axis is what? What is x-axis in this figure? X-axis is time. Okay. So the independent variable is time. But the time is discretized. Time is discretized. We don't know what is the signal amplitude at 0.25 seconds? Do you know from the figure? Can you say that what is the signal amplitude at 0.5 second or 0.25 second here? It is undefined, right? It's undefined here. So at 0.25 or any other value in between 0 to 0.5, at 0 you know the value is 0. At 0.5 the value is something, right? Which I have not written here. So this is 1 volt, or let's say this is 2 volt. This is another 1 volt. So here you see that, all right, I have written this ranges like this. It can assume any value along the y-axis. It's not necessarily 1, 2, 3, 0, -1, -2, minus. It can take 1.2 or 2.1 or any infinite values along x-axis, along y-axis. So you just observe the x-axis. Observe the x-axis in between 0 to 0.5. Are there any accepted y-axis value?
No, sir.
No, right? So here we don't have any accepted x-axis value. Here also we don't have, right? Here also we don't have. So for these all time values, the y-axis values are not present in the figure. Okay? Or we can say the x-axis is accepting some finite set of values. The x-axis is accepting some finite set of values. So here you can write one finite set of values. Finite set of permitted values, right? So the x-axis can be 0, 0.5, 1, 1.5, 2, 2.5, 3, 3.5, 4.5. So I have taken the starting and ending point 0 second to 5 second as like the last thing. 0 second to 5 second. In between 0 second to 5 second, how many permitted values are there? How many values you can see here, including both 0 and 5? It's 1, 2, 3, 4, 5, 6, 7, 8, 11 values are there. Right? 11 values, 11 permitted values are there. There are no other values for which the value of amplitude is defined in the student. This type of signal we call it as a discrete signal. So it is discretized along with the trip. It is discretized along with the trip. Y-axis, isn't it? Sorry, x-axis. It is discretized along x-axis. So x-axis is our time, so we call it as discrete time signal. Now comment regarding the y-axis. What you can see in this figure. It's red color. And let's suppose this peak is somewhere here. Okay. And this peak is somewhere here, greater than 2. Okay. This peak is somewhere here, and this peak is somewhere here. This peak is somewhere here. Okay. So what we can see, y-axis is capable of assuming how many values within the given bound. Let's say the given bound is -3 to 3. I'm taking -3 to +3. So in between -3 to +3, how many values are permitted and how many values it can assume? Y-axis. Can someone answer? Y-axis. How many values?
X-axis values like that one. Same.
Infinite values, isn't it? It's not discrete. Like you can see, you can have this value as 0.9, this value as 1.1, this value as 1.95 or whatever, isn't it? Any value within this range, any value it can assume for a given value of time. So how many value of time you have? You have 0 second, 0.5 second, 1 second, 1.5, 2, 2.5, and so on up to 5. So for these values of time, what can be the y-axis value? The y-axis value can be any value within 3 volt to minus 3 volt, any value. It can be minus 2.95, minus 2.9999, minus 1.01, anything, right? So in this figure, y-axis is continuous, isn't it? Y-axis is continuous because y-axis can assume any value within a given bound. So along any axis, if the signal is capable of assuming any value within a given bound or infinite possible value within a given bound, we call it as continuous. Okay. So in this figure, what you can see, it is continuous along y-axis, but it is discretized along x-axis. Is it clear to all of you? This signal is continuous along y. Continuous along y-axis, but it is discrete along x-axis. Continuous along y-axis, it is discrete along x-axis. Because y-axis is capable of holding infinite possible values, whereas x-axis is capable of holding 11 values only. Right? We don't have any values that in x-axis except this 11 points, right? That can have a y-axis value. So this type of signal is called as discrete time signal. Next two other versions we will see. We have seen previously, which is called as continuous time signal. In the previous slide, this is continuous time signal. I spoke about continuous along x-axis, time axis. And in the next figure, here I have shown it is discretized along x-axis. What will be the mathematical representation? It is discretized along x-axis. We cannot write it like x of t anymore. This t is discretized now. We can write it as x of nt. So nt. So what is this capital T and what is this n? This capital T is this period, which is repeating. Okay? The T is here 0.5 second. So x of 0t, 1t, 2t, like that. You can, so if you put n is equal to 0, so it will be x of 0. If you put n is equal to 1 and t is equal to 0.5, you will get x of 0.5. Then you will get x of 1, x of 1.5. So for these all values of the function, we have a y-axis value present. This is called as discrete time signal. X-axis is discretized. Remember, x-axis is discretized. So what we have seen continuous time signal, and we have seen discrete time signal. And what is continuous and discrete here? And what is time here? Time is the x-axis parameter, right? It is the x-axis parameter, that is the independent variable. That is the independent variable. So there is a technique which is used to convert this continuous time signal to discrete time signal. From here to here we can convert using a technique called as sampling. Using a technique called as sampling. So a sampling technique is used to discretize x-axis or discretize time axis. Remember, this is an important thing. Sampling is an important phenomenon. Why sampling is used? It is used to discretize sampling along. continuous time signal, discrete time signal. It is, I guess it is clear to all of you. We are speaking of the x-axis value or the independent variable value within a given bound. Let's say the t is defined within a given bound. Let's say t1 to t2. So within this given boundary, if infinite possible values are there, it is continuous. If it is finite, it is along x-axis only. So that's why the x-axis name is here, continuous time, discrete time. Similarly, we have continuous amplitude, discrete amplitude. Okay. It's clear? Anyone having a doubt? So I will assume that all of you understood. Continuous time signal, for every value of time, we have y-axis value present. Discrete time signal, for discretized value of time, we have the y-axis value present. Y-axis value can assume any value within a given boundary for both the cases. Okay. For both the cases, y-axis is continuous. Here we are speaking about continuous time and discrete time. We are speaking about continuous along x-axis and discretization along x-axis. So what is the process that is used to do this? It is called as the sampling process. Sampling process is used to discretize the signal along x-axis. Sampling is used to discretize the signal along x-axis. We have another process to discretize the signal along y-axis. We call it as quantization. That we will see in subsequent lecture. Okay. So let me give you some break of around 10 minutes. We will meet at around 4 o'clock. Meanwhile, you can just have a look to this. Next type of signal classification. We have seen the signal which are discriminated as continuous time signal and discrete time signal, which considers the x-axis of the independent variable and classify them based on the independent variables capability of holding infinite possible values, a finite set of possible values within a given bound or within a given range. So if it is infinite values are can be permitted within a given range, we call it as continuous along time, or if it is capable of holding an infinite set of values, we call it as discrete time. Similarly, another classification we have, we call it as continuous in amplitude. And we have another version which is called as discrete amplitude. So amplitude happen to be the y-axis parameter, right? Which is the dependent variable. So amplitude is dependent on some independent variable. Example is time. So this amplitude can be any voltage signal or current signal or any other temperature or pressure or any real time event. So this continuous in amplitude, there is some other name. We call it as analog signal. And discrete in amplitude, the name is digital signal. Continuous in amplitude, the name is analog signal, and discrete in amplitude, name is digital signal. So a signal that is continuous in amplitude is called as analog signal. Signal which is discrete in amplitude is called as digital signal. So if the y-axis, we will see there is a special form of digital signal which we are interested in, where the y-axis is capable of holding only two possible values, either high or low, or let's say 5 volt or 0 volt, right? So that we call it as binary signals, which you handle in the physical logic design thing, right? Ones and zeros. Let's take an example and visualize how analog signal looks like and how digital signal looks like. Let me take an example here. I will show Forces like the amplitude, which can be either voltage, voltage or current or temperature, which is going to be dependent variable that is dependent on time. So I would like to plot continuous in amplitude signal. Continuous in amplitude means what? Within a given boundary, let's set this boundary within this given boundary. If y-axis is capable of holding infinite possible values, then we call it as number. So let's say I'm plotting this. This is an example of analog signal. It means what? Y-axis value, you can see y-axis value at various instances of time. Let's say at this instance of time, what is the y-axis value? At this instance of time, there is some y-axis value. It can be anything. Let's say this is 5 volt, this is minus 5 volt. So between 5 volt to minus 5 volt, this can be any value, right? Where y-axis is capable of holding infinite possible values within a given time. Y-axis is capable of holding infinite possible values within, let's say, minus 5, within minus 5 to plus 5, so minus 5 to plus 5. Let's assume this is a voltage signal. So how many possible values are there? Infinite possible values. This is called as y-axis is continuous. So continuous time signal, we have seen that in between this 0 to 5 second, t is capable of holding infinite set of values. So irrespective of t holds infinite or finite set of values, if the y-axis is capable of assuming infinite set of values within a given boundary, we refer that it is continuous along y-axis. We refer that it is continuous along y-axis. So whichever is continuous along y-axis, we call it as a continuous amplitude signal or analog signal, right? So this analog signal can be a discrete time signal, right? It is not always analog signal will be continuous time signal. Don't confuse. Analog signal, we refer to the analog. Analog means continuous in amplitude. Remember this one. Analog means continuous. Digital means which is discrete in amplitude. We are speaking here by taking y-axis into account. The axis which is holding the dependent variable. Based on that, analog or digital, you can say. Not based on the independent variable axis. Based on independent variable axis or time axis, we can say discrete time signal or continuous time signal. Based on y-axis value, we can say continuous in amplitude or discrete in amplitude. If it happen to be continuous in amplitude, irrespective of the x-axis thing, we call it as analog signal. And if it is discretized in amplitude, we will take one example, call it as discrete. Let's take an example for this. to execute the time. Plot the signal. I have certain signal. This is 5 volt. This is amplitude. Now you can see for any given value of time in this figure, for any given value of time, y-axis can be either here y-axis is 5 volt, here also y-axis is 5 volt, and here also y-axis is 5 volt, here y-axis is 0 volt, the column is 0 volt, and here for this time also it is 0 volt, for this time also it is 0 volt. So y-axis can be either 5 volt or 0 volt. This is called as discrete in amplitude. So amplitude within a given range, 5 or 0, or within -5 to or -6 to 6, y-axis is capable of holding only two possible values. It can be either 5 volt or it can be either 0 volt. There are no other values present that can be accepted as a valid y-axis value. This is called as discrete in amplitude. And this type of signal is called as digital signal. Another example of this digital signal, let me take another example. Right? Okay. Y-axis I will represent amplitude. So I have y-axis 5 volt, 10 volt, -5 to 0. Now let me plot a signal which is this type. So, what kind of signal it is? We have already learned 4 type of classifications, out of which what we can say the signal. Let me write this signal as RFP. So what we can say? Someone answer?
So digital signal.
Digital signal. Nasir Khan? Nasir Khan.
Sir, your voice not visible means.
Sir, your voice is not audible, sir.
Sir,
I'm calling Nasir Khan. Electrical one. Is it audible now?
Yes, sir, yes.
Nasir Khan, respond. Someone answered digital signal. Who is that? May I know the number?
Sir, it's me, sir. Sir, 2033.
So 33 told that it's a digital signal. Any other answer? Anyone else? 30, roll number 30. See. Roll number 30.
Yes, sir.
So, what type of signal it is? Okay.
Yes, sir. Sir. So digital signal.
That any other answer? Someone answered it as digital signal. Any other answer is there? $59. You see 59.
Yes, sir.
What type of signal it is? We have done 4 type of classifications out of which it fits into which category. Someone answered digital signal. Do you agree with that?
Yes, sir.
Which signal we call as digital signal? Signal we can call it as digital signal. Now I know. Right?
Sir, your voice is not clear, sir.
So discrete digital,
Which signal we can call as a digital signal?
so can't it be discrete?
A continuous digital signal.
Continuous time signal also.
So,
So discrete time signal.
discrete time. How for time you can see, let me write this is 10 seconds. In between 0 second to 10 second, you have all possible values of time, right?
Yes, sir.
So, it cannot be discrete along x-axis.
It's a continuous time signal.
First look to the x-axis. For x-axis in between 0 to this 10 second, how many values are permitted? Infinite possible values, right?
Sir.
In x-axis in between 0 second to 10 second. Infinite possible values are permitted. You can see all values are there, right here, anywhere. And there is a y-axis value associated into that. So from this, it is evident that it is continuous
Time signal.
time. Continuous in time. And now look to the y-axis. Y-axis within the given boundary -10 to +10. How many values are permitted? You can see 5 values are permitted, right? It can be either -10, -5, or 0, or 5, or 10. Can it be 1 volt, or can it be 2 volt, or can it be 9 volt, 9.3? No, isn't it? So in y-axis, it is discretized. So we call this type of signal as continuous in time,
In amplitude.
discrete in, isn't it? So continuous in time, discrete in amplitude. So anything that is discrete in amplitude, we can call it as a digital signal. Whichever signal which is discrete in amplitude, we can call it as a digital signal. Okay? So this can also be called as a digital signal. So this is also valid. This is also valid. Continuous in time, discrete in amplitude. Continuous time, discrete amplitude signal we can call it. Another example, let's take this is amplitude axis. We are taking for 10 to 10 from 0 to 10 and it's plotted. It is the signal, and let me define this. So what kind of signal it is?
Analog.
Analyze the x-axis first. Is it continuous along x-axis?
Yes,
In
sir.
between 0 to 10, there are infinite possible values along x-axis. Okay. So this blue color 10 is in second. This red color 10 is in third. So 0 to 10 second, there are infinite possible values that x-axis can assume. So
Yes.
what we can write for this signal? We can
Continuous
write
in
this
time.
signal. It is continuous in time. Continuous. And now look to the y-axis. In between minus 10 to 10, it can assume any value, right? It can assume any value given.
Yes,
So
sir.
it's continuous in amplitude. Continuous in time, continuous in amplitude. So whichever is continuous in amplitude, we call it as analog signal. So in short, we call the signal as continuous analog. This is the very correct expression for this. Called as continuous analog signal. So whenever someone asks you, states you, this is an analog signal. So by default, it should not be assumed always that all analog signals are continuous in nature. Okay. Analog word represents it is continuous in y-axis. Always remember. Analog word represents it is continuous along y-axis. We don't know about the x-axis value that need to be analyzed. So if it is continuous along x-axis also, we call it as a continuous analog signal. So always you should not be confused in between continuous analog and simply analog signal. Some textbooks usually refer continuous analog signal to the analog signal only. So based on circumstances, you see the characteristic of the signal and answer. Okay. Let's take another example. I will do this time amplitude. And y-axis This is minus 7. So what kind of signal this is?
Discrete.
Discrete analog.
Analog.
Discrete time signal.
Discrete.
Discrete times.
So always try to represent taking both axis into consideration.
Discrete in time and continuous in amplitude.
Yes. First, look to the independent variable side. So it is discrete in time. Okay. So you can write it as this discrete in time. And what about the y-axis? Y-axis is capable of y-axis is capable of holding infinite possible values. Right. So y-axis is capable of holding infinite possible values in between -7 to 7. Right? You can assume any value. There is no fixed value along the y-axis. So it is called as discrete in time and continuous in amplitude. Continuous in amplitude means what?
Analog.
It's analog. So this we call it as discrete analog. We call it as discrete analog. So we are representing taking both the axis into account, x-axis as well as y-axis. It is discrete in time, continuous in amplitude. The previous example, what we have seen, it is continuous in time, continuous in amplitude. So we call it as continuous analog signal, which is discrete analog signal. And this version you can see, this is the digital signal, right? Which is discretized along y-axis, but continuous along x-axis. This is called as continuous in time, discrete in amplitude, or call it as digital signal. Okay. Let's walk through. So we have studied today 4 classification of signals. We considered it here. Yes. We have 2 axes. In one axis, we take dependent variable that is in the y-axis, and in the x-axis, we take independent variable. Right. So here, independent variable. And here we take dependent variable. So based on the continuity of independent and dependent variable, we have seen 4 different classifications. Right? So if x-axis is usually taken time is continuous, we call it as continuous time signal, short time signal. Call it as continuous time signal. So if x-axis is time is discrete, we call it as discrete time signal. Now, if y-axis, that is the amplitude axis, is continuous, we call it as analog signal. And if y-axis or the dependent variable axis, which is usually amplitude, is discrete, we call it as digital signal. Clear? So these are the 4 classifications that we have seen today. Continuous in time, continuous in the first one is continuous in time. Okay, this is continuous in time. This is discrete in time. This is continuous in amplitude. This is discrete in